Okay, we are on lesson 6.1 on estimating finite sums. So as we did our lesson previously, all our equations were nice and linear or semicircles or whatever it is to create a nice geometric shape for us to figure out the area under the curve, right, between the curve and the x-axis. Now, as we know, the functions that we are facing are not always going to be linear. So how are we going to figure out the area between the curve and the x-axis when it's not a linear function? So we developed these approximation methods. So here you have your left rectangular approximation method, the right rectangular approximation method, and midpoint rectangular approximation method. At this point, we're going to start calling them LRAM, RRAM, and MRAM because it's a lot easier to call them that. And these are approximations. We're going to use rectangles to help us figure out as close as we can to the actual area under the curve. So first thing we're going to do is going to look at this function here, f of x equals negative x to the fourth minus 2x cubed plus 2.29x squared plus 3x plus 2. So you're going to graph this, but no, I don't expect you to do this by hand. You can have a graphing calculator out and punch it into the calculator to look at the function itself. As you're punching it in, you should see the graph looks something like this. It's like a M, right? So now we have an idea of what the graph looks like. Next, I want to make sure we plot out our x and y axis accordingly so that we have no space. So the recommendation is to plot every 4 boxes as 1 on the x-axis, and then every 2 boxes as 1 for the y-axis. We're going to do that for all 3 graphs here because we're actually doing the same exact graph in all 3 of these Cartesian planes. We are just simply using 3 different methods to do the approximation, and we're going to show you how to do these approximations, right? So that's the whole idea of today. So here are my scales being done here. And as I pull up my graphing calculator, I can see what my values are going to be. Well, the function here says we're going to start at -2 and we're going to end at 1. Now, how do I make my increments? How big to make my t-table? The trick is to get it from the intervals and the number of rectangles. This tells you how many rectangles we want. We want 6 rectangles between the numbers of the x values of -2 to x value of +1. So how do we figure out the base? How do we figure out the horizontal increments? Is simply taking b minus a divided by the number of rectangles we want. So in this case, it's going to be 1 minus -2 over 6. That'll give us 3 over 6, which is 1/2. So that means if I go -1.5, -1, -0.5, 0, 0.5, and look, it works perfectly and gets us to 1. Now, put the equation in your calculator, grab out your t-table, and find your values, find your y values. So if you use your t-table, you will see that your y values will fit nicely into this t-table. So my first y value is 5.16, 4.34, 2.29, 1.26, 2, 3.76, 4.29. Okay, and now you're going to use these points to plot out your graph on all 3 of these Cartesian planes. So make sure they are all the same. So now what you want to do is you want to mark the beginning and end of your area that we're looking at. So the beginning is -2 and it's going to end at 1. So like we did 2 days ago in our lesson, we're going to mark the beginning of -2, mark the end of 1, -2, 1, -2, 1. And don't forget your x-axis is the other part of your enclosement. So you using a highlighter can see that our area, the area that we're looking for, is this really weird curve that we have between the x-axis and my function. And as you're shading this, you can see this is not a nice geometric shape. So we cannot use what we did in the last lesson where we get to use our geometry and using formulas of triangles, rectangles, or even semicircles to help us. So that's why we have these approximation methods to kind of help us approximate the area that we want here. So the highlight kind of helps us see this is the region. And we're going to use color pencils to help us see how our approximation, is it good or is it not good, right? So start with the first approximation method. This is what we call LRAM. So you want 6 rectangles here. You go through your increments that you created before. So if you go through the increments, you'll see that we'll make 7 marks, but 6 increments, six spaces for rectangles. It is called LRAM because when you go to the first spot, you're going to go up these 2 edges to make your rectangle. But then you have 2 choices as to how to cap your rectangle, right? So you can either use the left side and make my rectangle this way, or I can use the right side and make my rectangle this way. Well, let's call it LRAM. So we're going to use the left end point to make my rectangle. So I'm going to go up from the left-hand side, use the left end point, and then come straight back down. That's my first rectangle. Next set, same thing. I'm going to go up the left-hand side, go to the right, and make my rectangle. Go up the left-hand side, go to the right, make my rectangle. And you can see as I'm drawing the rectangle, we are overestimating right now. And that's okay, because it's going to even out as we go on with this picture. See the next picture here, we now start to underestimate because of the way the graph curves. So it is okay for you to over or underestimate. And in fact, if you want to use color pencils to shade it, it'll be even clearer to see, oh, this is really an overestimation. It covers more than my graph. And this is an underestimation on this right-hand side. Okay, so to remind ourselves of this method, we're going to go back up to the explanation of LRAM and just remind ourselves that what do you do here? You use the left endpoints to make your rectangle. So to remind yourself, you really are drawing to the right. You're drawing to the right to create your rectangle. And the whole idea of this is to calculate how much the rectangles are so that it can be used to approximate the actual yellow area that we're looking at. So what we're doing here, we're going to take the rectangles and add them up. So add up base times height, base times height, base times height. But to make it quicker, because since all your bases are exactly the same, your bases are half, right? Half units apart. So you can go ahead and factor that out, right? Factor that out and simply add all the heights together. So the first height is actually my first y value here, so 5.16. Second height is the second y value. Third height is the third y value. And you will see in our picture, we use every single y value except the last one. So you're going to use all your f of x values except last one. Okay, and then putting this in the calculator, because again, I don't really want you to spend time doing this. So 18.81 and your approximation for the first method would be 9.405 for the area. Okay, all right. As we discussed in the previous, in the LRAM, you know you have 2 options when you're drawing your rectangle. So you have the option of using the right side. So that's what RRAM is. RRAM says, okay, now I'm going up my rectangle, but I'm going to go up on the right-hand side, go backwards, and complete my rectangle this way. Up the right-hand side, go backwards. And as you can see, LRAM and RRAM are actually exact opposite behavior of each other. My LRAM started off with overestimating. So my RRAM is now going to start off underestimating. And it's going to switch off later on. So you see your RRAM is looking like so. You're underestimating first, and then you have a little bit more overestimation here. Okay. Now LRAM, RRAM, which one is better? There is no way to figure out which one's better because it really depends on the curvature of your graph. So LRAM and RRAM are really neck to neck in terms of how good of an approximation they are, right? So same as before, we're going to write our little note here and say use the right endpoints to make our rectangle. We're going to draw to the left this time. And you can see in the picture, we used all our f of x value, our y values, except the first one. So I usually tell my students and say, all right, well, how do you remember this? LRAM, you don't use the last one because they both start with the letter L. So LRAM and last. And the RRAM, you don't use the first one because they both have the letter R. So RRAM and first. So hopefully that will help you remember that. All right. So the area of this is 1/2. Don't forget we don't use the first one. So we start with the second one, 4.34, 2.29, 1.26, 2, 3.76, and 4.29. All right. That will get us, 17.94, which is an approximation of 8.97. Okay, so one was 9.405, one was 8.97. They're not too far off each other, right? Usually I use money to kind of help me see the comparison. They're off by less than 50 cents. That's okay. That's a pretty good approximation. Okay. All right, so now we're down to the last method. What is this Mram? So remember how we were saying we need 6 intervals for our rectangles, right? So our 6 intervals for our rectangle because we want 6 rectangles. But we already used the left side, we already used the right side. How do we get this other one? This is Mram. So you want to go in between your graph here, go all the way up to the middle between the left and the right endpoint, go to the middle, this is the midpoint, go up to the function itself, see how where I marked that, and now you draw your line both to the right and to the left. And you'll see that within one rectangle, most likely you will have some over and some underestimate, right? So again, the trick is to go between the two endpoints, go all the way up to your function and draw that height first, then finish your rectangle. A lot of times students struggle with this because they want to draw from the left and the right end, and it's really hard. So again, I recommend that you find your midpoint first, draw across, and then come down. Find your midpoint, draw across, come down. Midpoint, draw across, finish your rectangle, and lastly, finish your rectangle this way. And you'll see this approximation is kind of fun because it has a little bit of over and a little bit of underestimate in each of the rectangles. So hopefully this is better. In fact, when you line this up, Mram is better than LRAM or RRAM, but we don't always have that choice. So let's talk about that in a minute, okay? But this is my estimation. As you can see, I think my empty space and the filled in space are a little bit better evened out this time, okay? So I'm gonna remind myself that you use the midpoint to make your rectangles. You wanna draw to both sides. So left and right. And since your t-table, your first t-table, you already used the first and then you already skipped the last. So what are you gonna do? You're gonna create a new t-table. Create a new t-table with a new midpoint start point for your t-table. So where do you start? You start in between these first two. So what's the number right in the middle of -2 and -1.5? -1.75. And then the good news is then you can use your t-table on your graphing calculator. The increments are still the same because if you look at it, the next midpoint is exactly 0.5 away, 0.5 away, 0.5 away. So you know that that's -1.25, -0.75, -0.25, 0.25, and 0.75. And all these numbers are in between each of the X values that we had in the previous t-table, right? So now go to your calculator, use your t-table, go back to table set it to start at -1.75 and make your delta table, your change in table 0.5. And now your t-table has new values. You have 5.1, 3.29, 1.57, 1.42, 2.86, 4.38. And now I don't have to worry about skipping the first or skipping the last because there's exactly 6 values here. So these are our 6 rectangles. So our area is still 1/2. Our increments always stays the same. So 1/2, 5.1 plus 3.29, 1.57, 1.42, 2.86, 4.38. Okay, and now let's see what that gives me. We got 5.1, 3.29, 7, 1.42, 2.86, 4.38. Okay, that's 1/2 of 18.62. So this approximation gives 9.31. So this is a lot closer than the other two answers. Now your MRAM answer is most likely going to be in between LRAM and RRAM, but it won't be exactly half. It could be coincidence, but it's not always the case, right? So MRAM is going to be somewhere between LRAM and RRAM. So that's a good check for yourself to see if you're on the right track, okay? All right, so this is really good to see how to do it when you are given a function. So we were given a function here to start with, and we're able to find the y values to help us do these approximation methods. Now, when is this actually useful to us? When we actually don't have a function, when we have to use data points like this. So this is a data point, this data table. It is trying to look at a vintage sports car accelerating from 0 to 142 miles per hour in 36 seconds. So you're looking at your car speedometer and you say, okay, at 1 second, my speed is 40 miles per hour. At 2 seconds, my speed is 62 miles per hour. Now you can't say in between those, I must be exactly, I don't know, 51 miles per hour. You don't have enough information to say that, right? So that's why we don't have the information for MRAM in this case, because you don't have enough information to guess the y values there. So when that happens, your direction will say, oh, use rectangles to approximate, to estimate. That means you're doing both LRAM and RRAM, and then you average, so you divide it by 2, and that will give you a better approximation. So the way this is done is if you plot your velocity, you plot these data points onto a graph like they did in the picture below. If you plot your velocity like so, then the area below the graph and between the x-axis and the graph is the distance that you have traveled, or whatever this object has traveled. So the area we're looking at is this. This region right here is going to tell us how far this car has traveled in the 36 seconds, right? So again, it's not a really perfect geometric shape, so we can't use like triangle to do this. So that's why we have to use LRAM or RRAM to approximate it to see what my what distance I have traveled in the 36 seconds, right? All right, so first graph, I would like us to do LRAM, right? So I'm giving you enough space to do that. And then the second graph, I would like us to do RRAM. And you're going to use the same increments that the T-table gives you. So each graph, each box is one rectangle. And because it's LRAM, the very first value is 0. So the very first rectangle is actually just flat. It's a line, right? And second rectangle is going to be right here. Remember, left side, left endpoint. So I'm going to use my left endpoint to draw my rectangles. Left endpoint, left endpoint. You see, because of the way this graph is curved, my LRAM is completely under the curve. This is another word for this is these are inscribed rectangles. Okay, so these are inscribed because they're completely under my curve. Whereas in the previous example, some of my rectangles are out, some of my rectangles are in, but this one, all of it is underneath. So these are inscribed rectangles. All right, so my estimation here is going to be completely underestimate, and that's okay. All right, I'm going to figure out the area of this, or the total distance. So the area of this is 0.001. That's my width here, because every single increment's up by 0.001 or 1 second. And then you add all your y values except the last one, because this is LRAM. So 0 plus 40, 62, 82, 96, 108, 116, 125, 132, 137. All right, so let's see, 40, 62, 82, 96, 108, 116, 125, 132, 137. I get an approximation of 0.898 miles. And we know that because it's miles per hour times hour, so your final unit is miles, right? Don't forget, it's a completely underestimate, so we're going to go back to RRAM to see what my overestimate will look like. All right, so RRAM, you go up on the right-hand side, go backwards and find my rectangle, right-hand side, backwards, right-hand side, backwards. So for RRAM, we're going to use the right-hand side and go up and finish out my rectangles. One of my students in class asked and said, hey, can I just go ahead and start on the right-hand side and draw my rectangles? You can, if that's what you want. Just, make sure you're going the right direction, right? So again, this is my RRAM, and you can see it is a completely overestimate for this one, which is good. It's going to balance out my underestimate for that one. So when something is completely overestimating your entire graph like that, it is a circumscribed rectangle. These are all circumscribed rectangles to cover the outside of my function, right? So my area of this is 0.001, still the same width. You're going to add everything except the last one, which, except the first one, which is fine because the first one is 0. So it really doesn't do anything for us, but it's the same rule. So let's go ahead and put that in. We get 0.001 times 1040. So that is 1.04 miles. So to answer our first question, using a rectangle to approximate these, we're going to have to find the average of these two, right? So 0.898 plus 1.04 divided by 2. So, oopsies. And then divided by 2. Our approximation is 0.969 miles. So it took about 1 whole mile for this race car to reach its maximum power, maximum speed of 142 miles per hour, right? I've heard from other students that this is not so good. So I don't know much about sports cars. I guess this is not the best. All right. Moving on to the next question. It says, approximately how many seconds did it take the car to reach halfway point? Well, let's figure out what the halfway point is. We take our approximation from the first part, divided by 2. Halfway point is about 0.485 miles. So that's the magic number we're looking for. All right. So don't do this on your paper because you already drew this in, but I'm going to erase my rectangles here so you can have a better idea of what we're talking about. So remember, we talked about the fact that our area is this. This is the whole 9.69 miles. So where is it halfway? Well, normally students would say, well, okay, go ahead and just cut it in half. Well, if you cut it in half right here, this is a curve. This is not going to be exactly half because this piece, you can tell, is smaller than this piece, right? So then because of the way my values are on my data table, if I make the cut here, that's not halfway. So my only choice is then to move on to the next one. Can I make the cut here? Would that be a better halfway? So if I make the cut right here, is this a better halfway? We're going to check. If that's not good enough, then we're going to move on to the next number. We're going to cut it at 0.07. We're going to cut it at the 7 seconds or cut it at 8 seconds to see which one gets us as close to the halfway as possible. So you're going to do a really quick RM, LRM to see if you get a good approximation. Because again, we don't know the exact number. So we have to use these two approximations to help us see if we can get the number we want. So a quick LRM will say 0.001. And then 0 plus 40 plus 62 plus 82 plus 96 plus 108, right? That's 0.001. So 40 plus 62, 82, 96, 108. So 388. So this is 0.388 miles. Okay, Ms. Chu, that's really small. I get it, but because we knew that's going to be a completely underestimate. So let's see if the RM is going to help us. RM is going to be 0.001. 40 plus 62 plus 82 plus 96 plus 108 plus 116. That gives me 0.001 times 504. So that gives me 0.504 miles. Okay, now we're going to average these two because that's my approximation, right? So 0.388 plus 0.504 divided by 2. That gives me 0.446 miles. That's very good. That's very close to my halfway point. I know that if I were to make the cut at the 7 seconds, I'm going to be way too much because that's way beyond the halfway. So to answer the question, I will say, so in conclusion, when we're answering the question to this problem, roughly how many seconds did it take the car to reach a halfway point? Well, we know our cut is here at 0.006, but that is not 6 seconds. It is actually 0.006 of an hour. So what we need to do is go ahead and compute that and say 0.006, how many seconds in an hour? 60 minutes times 60 seconds, 3,600 to get 21.6 seconds. So then to answer the question, we'll say at about 21.6 seconds, the car reaches halfway with a speed of 116 miles per hour. Okay, that's it.